Okay, I hope I'm audible to all students who are attending this lecture of Mathematical Methods for Economics, Part 2. Okay, we continue with our lectures on integration. We continue with our lectures on integration. Formally, this is chapter 10 of the book I prefer to follow for the MME2 course, which is Sitsater and Hammond, the 4th edition. Okay, now all students can recall that in the previous lecture of integration, we were looking at the concept of how to find the area below the curve and above the x-axis. We had also looked at finding the area above the curve and below the x-axis. So we had done two cases in the previous lecture. I repeat, finding the area above the x-axis and below the curve, finding the area below the x-axis and above the curve. Okay. Now, in this particular lecture, we intend to solve problems from Sitsater-Hammond. So, problems section 10.1 of Sitsater and Hammond. Now, as per the 4th edition of this book, this is page 344 of Sitsater and Hammond. Okay, so let's solve the problems from this particular section. So let's look at question 1. Compute the area. Compute the area under the graph of f of x equal to x cube over 0 to 1. So very simple question. Let's quickly solve it. What will be the required area? There is no need to plot the graph unless the question mentions to plot the graph. Okay, so required area will be integral from 0 to 1 f of x dx, which we have learned from the previous lecture. Okay, so this will be integral 0 to 1 f of x is x cube dx. X cube ka integral is x to the power 4 divided by 4. We run this from 0 to 1. This is 1 upon 4 minus 0 by 4, which is 1 upon 4, which is my required answer. If in case students want to look at the diagram, I can draw a diagram for reference. All of us know that the x cube curve looks like this. Students who have attended my course, Mathematical Methods for Economics Part 1, you know that this is how f of x equal to x cube looks like. It passes through the origin, and when x is equal to 1, y is also equal to 1. So we need to find this area. This is nothing but integral from 0 to 1 f of x dx. F of x is x cube. All of us know, recall that integral x to the power n dx ka integral is x to the power n plus 1 upon n plus 1 plus the constant of integration. So in this case, x cube ka integral is x4 by 4. You run this from 0 to 1, you get the answer as 1 upon 4. Okay, then let's quickly look at the second question of the same exercise, which is as follows. Question 2. Okay, so again, guys, given the following functions, calculate the area over the given intervals. Calculate the area over the given intervals. Okay, so first part is given to us, f of x is equal to 3x square over the interval 0 to 2. Can we quickly find the area? I can say my required area will be integral from 0 to 2 f of x dx which will be integral from 0 to 3x square dx. What is the integral of 3x square? 3x cube by 3. Run this from 0 to 2. 3 and 3 cancel out. 2 cube minus 0 cube, which is 8, which is the required answer for this question. Okay, so hoping all students have understood this. Very easy, guys. Again, you can see it's a parabola. The rough sketches now you can draw at home, because I expect students attending this lecture to know how to draw rough sketches from the MME1 course. Okay, so part A is done. Let's look at question 2, part B. We need to find the area below the curve f of x equal to x to the power 6 over 0 to 1. So if we quickly solve this, what will our required area be? Integral 0 to 1 f of x dx. This will be integral 0 to 1 x to the power 6 dx, which is x to the power 7 by 7, which we run from 0 to 1, which is 1 to the power 7 by 7 minus 0 to the power 7 by 7. Okay, so this comes out as 1 upon 7, which is the required answer for this question. 1 upon 7. Okay, let's move forward to the next part, question 2, part C. These are very simple problems. So again, we need to find the area under f of x equal to e to the power x over the interval minus 1 to 1. Let's work this out. What will the required area be? Integral minus 1 to 1 f of x dx, which is integral minus 1 to 1 e to the power x dx, which is e to the power x ka integral. Please recall it's nothing but e to the power x only, which you run from minus 1 to 1. So this is e to the power 1 minus e to the power minus 1, which you can write as e minus 1 upon e, which is the required answer for this question. All students recall that e to the power x ka integral is e to the power x plus c, where c is the constant of integration. And then guys, let's quickly look at question 2, part D. F of x is 1 upon x square over 1 to 10. Okay, now let's quickly solve this. So how will I find out the required area? Directly apply the formula. Integral 1 to 10 f of x dx, which is integral 1 to 10. 1 upon x square I can write as x to the power minus 2 dx. X to the power minus 2 ka integral is x to the power minus 2 plus 1 upon minus 2 plus 1. Run this from 1 to 10. This is x to the power minus 1 upon minus 1, which we run from 1 to 10, which I can write as minus 1 upon x, which we run from 1 to 10, which is minus 1 upon 10 minus 1 upon 1. So this is minus 1 upon 10 plus 1. Our answer is 9 by 10, which is the required answer for question 2, part B. So with this, our question 2 of Sitseta-Hammond problems section 10.1 is over. Let's now look at question 3. So compute the area. Compute the area A, capital A, bounded by the graph, of f of x equal to 1 upon x cube compute the area bounded by the graph of this, the x-axis, and the lines x equal to -2 and x equal to -1. Okay, so we need to find the required area for this particular question. So guys, first of all, we need to figure out from the previous lecture, which case is this? Is this area coming in the negative quadrant or is this area coming out in the positive quadrant? Now, clearly you can see from the lecture that if I plot the diagram for this question, if you plot the diagram for this question, it comes like this. You can take values and plot x-axis. This is my y-axis. Okay. And x equal to -1 is this line. This is the line x equal to -1. Then we have, this is the line x equal to -2. And if you plot f of x equal to 1 upon x cube, it somewhat looks like this. It's downward sloping and convex. Okay, it is downward sloping and convex. So how do we find this, guys? If I find the first order derivative, so f of x is 1 upon x cube, which is x to the power -3. First order derivative is -3 x to the power -3 -1, which is -4. So -3 upon x to the power 4, which is negative, therefore downward sloping. And guys, if you find the double derivative is -3 into -4 x to the power -5, which is 12 x to the power -5. Okay, which I can write as 12 upon x to the power 5, which is negative. Why is it negative? Because x is negative. X lies between -1 and -2. So x, you can see, is negative. If x is negative, 12 upon x to the power 5 is negative. Therefore, concave. So the graph is downward sloping and concave. So I need to find the required area. This is my required area.
So,
Yeah, 1 minute before asking the doubt, let me quickly explain this and then I'll be catering to your doubts. Okay, so I am again explaining it. We are given the function f of x equal to 1 upon x cube. We need to find the area bounded by x-axis and the lines x equal to -2 and -1. Now draw the line x equal to -1, draw the line x equal to -2. How will I plot the graph f of x? Check out the first order derivative. It's less than 0. X to the power 4 is always positive because 4 is an even power. F dash x is negative. That means the graph is downward sloping. F double dash x is also negative because x is negative from -1 to -2. That means the graph is concave. Now we need to find this required area. Okay. Okay. So now, guys, how will we find the area? Now this is which case? This is finding the area below the x-axis and above the graph. So how will I find the required area? Integral as x goes on from -1 to -2. Okay, so this is going to be integral as x goes on from, this is actually -2 to -1. We are going from here to here. Actually, we are moving towards the origin. So -2 to -1, small f of x dx. Okay, this will be our required area. Let me write it more clearly. So now let's evaluate this, guys. I am erasing this bottom portion of the screen and solving it here. Let's see what our answer comes out. Okay, so this is x equal to a, this is x equal to p. So a is -2, b is -1. F of x dx. Now this comes out as integral from -2 to -1. F of x is, guys, how much? X to the power -3 dx. What is the integral of x to the power -3? X to the power -3 plus 1 upon -3 plus 1, which we run from -2 to -1. So this is x to the power -2 upon -2, which we run from -2 to -1. Now put, so this further I can write as -1 upon 2x square. Running this from -2 to -1. Okay, now let's solve it on the top. So I can further write it as -1 upon 2 into -1 ka square minus -1 upon 2 into -2 ka square. But since this is the area below the x-axis, the whole term has a minus sign outside. I repeat, since this is the area below the x-axis, the whole term has a minus sign outside. So this is f of b minus f of a, where b is -2 and a is -1. But since this is the area below the x-axis, it has a minus sign outside. Now you know how to calculate the remaining part of the question. Okay, so I am erasing this off, moving forward. So this I can further solve. -1 upon 2 plus 1 upon 8. So this is -1 upon 8 minus half, which I can write as 8 being the LCM, 1 minus 4, which is minus of -3 by 8. Minus of -3 by 8 becomes +3 by 8. So my required answer for this particular question comes out as 3 by 8. Okay, so hoping all students have understood question 3. We had to compute the area bounded by this curve, x-axis and the lines. So you can clearly see, first we have drawn the lines x equal to -2 and x equal to -1. We have drawn a rough sketch of f of x. We solve it like the way we had learned in the previous lecture, f of b minus f of a. But since this is the area below the x-axis, it will also have a minus sign outside. This minus sign is taken to make the area positive, because if you look at the answer is 3 by 8. For my area to be positive, I am taking a minus sign outside, because area has to be always positive. Area cannot be negative. Now to make the area positive, that is why we have taken a minus sign outside. Okay. Now let's look at the last question for this exercise, question 4. Compute the area. Okay. Compute the area capital A bounded by the graph of f of x equals half e to the power x plus e to the power minus x, the x-axis and the lines x equal to -1 and x equal to 1. Okay, so we need to compute the area A bounded by the graph, the x-axis and the lines x equal to -1 and x equal to 1. So guys, how will we solve this particular question? Now clearly you can see something. You can clearly see that f of x equals half e to the power x plus e to the power minus x is always positive for all x belonging to real numbers, because the base is e and e is always positive. Now, any positive number, you raise it to any power, it will always be positive. That means what will the required area be? Required area will be integral from -1 to 1 f of x dx, which is integral -1 to 1. F of x is half e to the power x plus e to the power minus x dx. Half is a constant, it comes out of the integral. Okay, so now guys, what is the integral of e to the power x? E to the power x. What is the integral of e to the power minus x? E to the power minus x into -1. Now we run this from -1 to 1. So I can solve the remaining portion here. So this becomes half times e to the power 1 minus e to the power -1 minus e to the power -1 minus e to the power minus of -1, which is +1. So half times e minus 1 upon e minus 1 upon e plus e. So this becomes half times 2e minus 2 by e, which is nothing but e, because 2e divided by 2 is e minus 1 upon e. So the required answer for this question is e minus 1 upon e. Okay, so with this, our exercise 10.1, or I can say the problems of section 10.1 of Seta-Hammond are over. Now, any student who has a doubt till here, you can unmute your mics and you can ask. Okay, so after having completed the problems of section 10.1 of Hammond, let us now move on to the next concept within integrals, indefinite integrals. So first we have done the application. Now I'm going into the core of integration theory. So our heading now is indefinite integrals. Okay, so all students can write this statement. Integral of small f of x dx is equal to capital F of x plus c, where capital F of x is equal to, where capital F of x ka derivative is equal to small f of x. So we had done this indirectly in the previous lecture as well, that capital F of x is the antiderivative of small f of x, or I can say that small f of x is the derivative of capital F of x. So students can write where f of x, small f of x is called the integrand, small f of x is called the integrand, c is the constant of integration, c is the constant of integration. Okay, so hoping students are clear with the statement of indefinite integrals. If you integrate small f of x with respect to x, you get capital F of x plus c, where capital F of x is the antiderivative of small f of x, or small f of x is the derivative of capital F of x. Okay, now let us write the rules, or I can say important formulae for indefinite integrals. Rules or the important formulae for indefinite integrals. All students can write these rules. Rule number 1, integral of x to the power a dx is x to the power a plus 1 upon a plus 1 plus c, provided a is not equal to -1. Because if a becomes equal to -1, the denominator becomes 0, which is not defined. Okay, Second rule, integral 1 upon x dx is ln of mod of x plus c. That means integral of the function 1 upon x dx will be ln mod of x plus c. Third rule, integral e to the power ax dx is e to the power ax divided by a plus c, provided a is not equal to 0, because again, if a becomes equal to 0, denominator becomes 0, hence the expression becomes not defined. And then students can write the fourth rule, which is as follows: integral a to the power x dx is a to the power x divided by ln a plus c. Provided, guys, ln a should not be equal to 0. That means a should not be equal to 1 and a should be strictly greater than 0. All of us know that ln of 0 is minus infinity. So all of you know that when is the natural log function well defined? The natural log function is well defined if a is greater than 0 and the denominator is ln a, and ln a should not be equal to 0, which implies a should not be equal to 1. Okay, so hoping students have understood this. So there are 4 rules which we have done, and now students can write some important properties of indefinite integrals. Some important properties of indefinite integrals. Okay, so property number 1, integral a times f of x dx is equal to, always remember the constant comes out. If the constant is multiplied, then it comes out. So a times integral f of x dx, where a is a real number. This property is called as constant multiple property. Constant multiple property. Integral a times f of x dx is equal to a times integral f of x dx, where a is any real number. Second property, integral of a sum is the sum of integrals. So integral of f of x plus g of x times dx is equal to integral f of x dx plus integral g of x dx. Okay, similarly guys, I can write integral f of x minus g of x dx is equal to integral f of x dx minus integral g of x dx. Okay, so hoping students have understood this. And now guys, we can do some practice questions based on this, after which we stop in this lecture. So practice questions based on indefinite integrals. I am just doing some practice questions. Some of them we will be covering in the next lecture. So question 1, evaluate the following. Part A, integral x dx. Part B, integral 1 upon x cube dx. Part C, integral root x dx. Okay, so let's quickly solve them part by part. So integral x dx will be x to the power 1 plus 1 upon 1 plus 1 plus c, which is x squared by 2 plus c. Part B, integral 1 upon x cube dx, I can write as integral x to the power minus 3 dx, which is x to the power minus 3 plus 1 upon minus 3 plus 1 plus c, which is x to the power minus 2 upon minus 2 plus c, which is minus 1 upon 2x square plus c. minus 1 upon 2x square plus c. And guys, part C, integral root x dx, I can write as integral x to the power half dx. This I can write x to the power half plus 1 upon half plus 1 plus c. This is x to the power 3 by 2 divided by 3 by 2 plus c, which becomes 2x to the power 3 by 2. 2x to the power 3 by 2 upon 3 plus c. So my answer for the last part is 2x to the power 3 by 2 divided by 3 plus c. Okay, and similarly we can do one more practice question. Question 2. Evaluate integral 3x4 plus 5x square minus 2 times dx. Let's quickly solve this. So this will be 3x to the power 4 plus 1 upon 4 plus 1 plus 5x to the power 2 plus 1 upon 2 plus 1 minus 2x plus the constant of integration c. Remember, in indefinite integrals, your answer will always contain the constant of integration c. So I can write this as 3x to the power 5 upon 5 plus 5x to the power 3 by 3 minus 2x plus c, which is the final answer for this question. Okay, so guys, this is where I intend to stop in this particular lecture. Homework for all students is as follows. Homework for this lecture is evaluate the following. Evaluate the following. Part A, integral b upon r to the power 2.5 dr, where b is a constant. Where b is a constant. And part B, evaluate integral a plus bq plus cq square dq. So students, please take these last two questions for homework. You can discuss the answers with me on the WhatsApp group created for the MME2 course, or you can mail me your answers at divineschoolofeconomics@gmail.com. So guys, this is where I intend to stop. We will do 2-3 more practice questions on indefinite integrals, and I will be doing the concept of definite integrals more in depth in the next lecture of integration. So this is where I intend to stop. I hope all students have enjoyed this lecture. Any doubt, you can unmute your mics and ask, or call up, or mail me your doubts at divineschoolofeconomics@gmail.com. So this is where I stop in this lecture.